Hello students, welcome back. Now let's go to section 3 and complete these exercise problems. We completed these two. We have two more to go. By the way, these are all related to this grand summary. Even multiplicity, same sign, whether 0 or pole, it doesn't matter. Odd multiplicity, sign change. It doesn't matter whether it's 0 or pole. Even, same sign, odd, sign change. Why do we have those kind of behavior? Well, let's see. Zeros first. Hit and bounce back because that's the behavior of the power function that shares the same local behavior, which is the blue dotted curve. Or the other way around, hit and bounce back, either plus side or minus side. Either way, no sign change. Plus stays as plus, minus stays as minus. That's because the same behavior is going to be observed from the power function that shares the same behavior, same local behavior, and that's going to be x minus c to the m power times some constant. M is even, we're going to get something like this. Now, what if we have a pole or a vertical asymptote? It's going to be dragging toward positive or drag toward negative. Each side will drag each other. So we have plus plus or minus minus. Here, the red dotted curve represents a power function that shares the same local behavior. So some constant times 1 over x minus c to the m power. From there, we can get the property of this original function, the local property of the original rational function, and they both say the same thing, same sign around x equal to c. Now, what if we have odd multiplicity? For zeros, we have something like this. Hit and cross and continue increase, or hit and continue decrease, crossing the x-axis. We have sign change, either from minus plus or plus minus. That's for the 0. Now, for poles, we do not have any crossing. We just have split toward positive infinity, negative infinity, or negative infinity, positive infinity, either way. So minus plus or plus minus. Either way, same conclusion. So even multiplicity, same sign. Odd multiplicity, sign change. Okay, let's go back to this problem. Okay, how do we do this? Copy and paste this thing. Expand the font a little bit. Okay, how do you factor this? I don't know about you, but I cannot think straight if you have negative sign up front for the leading coefficient. So let me change the problem a little bit. Getting this negative out, all the way out, so that I can change signs here for each of these. Okay. And then you can go ahead and factor this. How do you do that? Numerator is gonna be relatively okay because I can factor x squared out. See, GCF is x squared, so I can factor it out. So x squared, and then that's just first power, and then all out, 0th power. How about the denominator? It doesn't work like that. We do not have GCF, so how do we handle the denominator? You can factor it with respect to x squared. So we have x squared minus 1 times 4x squared plus 3, like this. Now, if you have, say, 4y squared minus y minus 3, then you can factor it as y minus 1, 4y plus 3, like this. Exactly the same thing is going on, except that x squared is now y. So x to the fourth power is y squared. And then we can factor even further. This one can be factored as x minus 2 total quantity squared because it's complete square. And then here, this can be factored as x plus 1 and x minus 1. This one is reducible, so we can't do anything further. And I guess that's it. Actually, one more. And why did I keep it? I could have removed it in step 1 or step 2. Well, okay, let's remove this negative sign, multiply negative sign to both left hand side and right hand side, and flip it over. So in the end, this is what we get. So that's the same as this inequality in factored form. Blue will give me the zeros, and red will give me the poles. Okay, I did the prereq part for you. From this point on, stop the playback and go ahead. Use a sign analysis, the local property, whatever you learned here, and then try to complete the problem. By the way, here's a summary of what we just did, how to factor, and in the end, we got this, same as that. Okay, what do you have next? Zeros and poles. 0 comes from the numerator, poles come from the denominator, and the multiplicity is pretty simple. Second power, first power, that's it. Now these four numbers divide the number line into 5 pieces. So put those in, and then label them. Is everybody okay with this? -1, 0, 1, 2 in increasing order, and red, pole, blue, 0, and then they're all hollowed out because we are dealing with strict inequality. Nothing can be equal to any of those. We have multiplicities, odd, even, because we have multiplicities 1, 2, 1, 2. Alright, okay, all the hard part is now done. Let's do the sign analysis. As usual, let's start from positive here. Plug in a big number here, say x is 100 or something. 100 minus 2, 100 minus 1, things like those, they're all positive. So we begin with positive. And then cross even, same sign. Cross odd, change sign. Cross even, same sign. Cross odd, change sign. And that's how you can get this. Start from plus. Cross even, same sign, stay positive. Cross odd, change to minus. Cross even, stay minus. Cross odd, change to plus. Okay, alright. We want f of x to be positive, right? So take positive intervals. This, and there. There are 3 intervals put together, and we have the answer. We have graphs here, but I don't know whether they're going to be really helpful. Looks like that part positive, and then here, and then hit and bounce back. That part is positive as we see this local behavior, but I don't know. It's difficult. Graphs give us too much information, so often it is kind of difficult. diagrams are much easier to deal with. Okay, do we have enough time for the last problem here? Let's try. The left-hand side is the same as the previous problem, so we can manipulate pretty much the same fashion. Previously we got this, so that's basically the problem we are working on right now. Previously we had strict inequality, same direction, so we have that. The reason we can switch the order was because we removed the leading negative by changing all the sign to negative down here. Remember all that? Well, here's a reminder. And then zeros and poles, the same as before. And then the location of all these. Here we go. But this time, be careful. Even is not that important. Blue is 0 and that's solid. Blue is 0, that's solid because this is semi-inequality, so we have 0 numerator is perfectly okay. 0 equal to 0, that's fine. So solid dot, that's part of the solution set, no problem there. Denominator, on the other hand, there should be hollowed out because denominator cannot be 0. X equal to -1 and x equal to +1, they're not allowed in any case. And then we apply the sign analysis as before, plus, minus, plus by the same reason. Crossing even, same sign. Crossing odd, sign change. Okay, we are looking for plus intervals. Be careful about the endpoints. Okay, what do we have here? Here, negative infinity to -1. And then 1 to 2, and 2 to infinity. But you see, 1 to 2, that's coming from 0, blue, that's bracket. So I can join them together at the same interval like this. Previously, we had to separate those because x equal to 2 was not part of the solution set, so we had 3 separate intervals. But this time, we can join them together, and then we get just 2 intervals. Negative infinity to -1, and 1 to infinity altogether. How do you like this? Is everything okay? Actually, no, not really. There's still one thing missing. Find out. Anybody found out? Here is the solution set. There you go. X equal to 0, this one is also part of the solution set. It's not part of any interval, but the function value is equal to 0 here, and equal to 0 is okay because this is semi-inequality. So the correct solution set includes this 0 as well. Same as this, same as that, okay, but one more. Will the graph help? I don't know about that. Let's see. Positive here, positive there, and also at x equal to 0 right here, touch the x-axis, so equal to 0 there. So semi-inequalities can be rather tricky. But don't really panic. If you miss those kind of subtleties, you're not going to lose too much. Making something like 9 out of 10 or 8 out of 10, depending upon the depth and circumstance, it's not going to kill you. But then again, if you keep missing the extra points after scoring touchdown, in the end you may lose the game. Of course, scoring touchdown is much better than scoring just field goal or turnover and coming back, but still, extra points, everything counts.